2-meter Yagis for radio direction finding can be made from tape measures and are inexpensive and not hard to make. Which of the following describes a basic unterminated rhombic antenna? A. Unidirectional, 4 sides, each side 1/4 wavelength long, terminated in a resistance equal to the characteristic impedance. B. Bidirectional, 4 sides, each side 1 or more wavelengths long, open at the end opposite the transmission line connection. C. 4 sides, an LC network at each corner except for the transmission connection. Or D. 4 sides, each of a different physical length. The answer is B. Bidirectional, 4 sides, each side 1 or more wavelengths long, open at the end opposite the transmission line connection. What is the primary purpose of a phasing line when used with an antenna having multiple driven elements? A. It ensures that each element operates in concert with the others to create the desired antenna pattern. B. It prevents reflected power from traveling back down the feed line and causing harmonic radiation from the transmitter. C. It allows single band antennas to operate on other bands. Or D. It makes sure that the antenna has a low angle radiation pattern. Answer A. It ensures that each driven element operates in concert with the others to create the desired antenna pattern. Why is it advisable to use an RF attenuator on a receiver being used for direction finding? A. It narrows the bandwidth of the received signal to improve signal to noise ratio. B. It compensates for the effects of an isotropic antenna, thereby providing directivity. C. It reduces loss of received signals caused by antenna pattern nulls, thereby increasing sensitivity. Or D. It prevents receiver overload, which could make it difficult to determine peaks or nulls. Answer D is correct. It prevents receiver overload, which could make it difficult to determine peaks or nulls. And now for the subject of antenna systems. An SWR less than 2:1 on HF and less than 1.5:1 on VHF may be acceptable on HF, but is not acceptable on VHF. When the antenna is matched to the feed line, maximum power is transferred to the antenna, and standing wave ratio is minimized. The delta matching system is used to match a high impedance transmission line to a lower impedance antenna. The feed line attaches to the driven element in 2 places, spaced a fraction of a wavelength to each side of the element's center point. The gamma matching system is used to match an unbalanced feed line to an antenna. The feed line attaches to the center of the driven element and to a point that is a fraction of a wavelength to one side of center. The driven element of a Yagi antenna can be fed with a hairpin matching system. The center point of the hairpin is electrically neutral, and so is often attached to an antenna system's metal boom for mechanical stability. The stub matching system uses a short perpendicular section of transmission line connected to the feed near the antenna. Dimensions A and B are adjusted to provide a match to the antenna and the feed line. Coaxial cable is the most common type of feed line. It's easy to use. It matches the impedance of modern radio equipment, i.e. 50 ohms, although there is some loss of signal depending on the quality of the coax and, of course, cost. Laddered line, or twin lead as we used to call it, is not as commonly used today as coax, although ladder line has very low loss. The electrical length of a transmission line or antenna is not the same as its physical length. Waves move more slowly in the line than in the air. The velocity factor is also related to the dielectric constant. Notice the higher loss for RG58 at 100 megahertz than RG8 or ladder line. Our next subject is the Smith chart. When you learned about impedance, you learned that all impedance consists of two elements, resistance and reactance. When you plotted impedance, the horizontal axis was resistance. Inductive reactance was up and capacitive reactance was down. The hypotenuse connecting resistance and reactance is impedance. The Smith chart allows us to solve many impedance problems graphically. This is what the Smith chart looks like. Here is a picture of the guy who invented the Smith chart. This is a listing of many of the types of problems that a Smith chart can be used to solve. To form a Smith chart, we start with a circle of radius u. That circle is the R equals 0 constant resistance circle. Next, we add the x equals 0, reactance equals 0 axis. Then we start adding constant resistance circles. R equals infinity is at the far right, and all the circles pass through it. Now we add constant reactance circles. Let's review what we have so far. The resistance axis is the horizontal line going through the middle of the Smith chart from left to right. Here are the resistance circles. On the left is the short circuit resistance, which equals 0. On the right is the open circuit resistance, which is infinite. The top part of the graph is inductive, and the bottom part of the graph is capacitive. If you normalize all the impedance values that create a certain value of SWR in a 50 ohm transmission line, you will find that the points lie on a circle centered at the point Z minus 1.0 plus J0. This is called a constant SWR circle. As SWR gets bigger or smaller. Notice the wavelengths toward generator and wavelengths toward load points along the rim. These are for working problems that involve changing impedance along the transmission line. The chart is normalized. We start with Z equals R plus or minus JX and divide all three terms by some impedance value such as Z0. That produces Z sub n equals R divided by. If we add more inductance, it moves us clockwise along a circle of constant resistance.